Welcome back. I'm going to try to describe functions as built from smaller functions. If you've not watched the previous video, I would recommend seeing the video on why it is we need stronger notions of functions to begin with, and the ways that set theory definitions can let us down and lead us into places where we don't have functions well defined, but we're still using them as if they're functions. But I'll leave that to that video. What we have now is one way to build up functions from a very primitive notion, one that we could use, say, in the language of logic, is to think of functions built on simpler ones, built on simpler ones. But we have to start somewhere. We need to know what are the atomic functions in this process. This may be familiar to anyone who's programmed. We think of a program as running our operations, but we understand that actually each one of those operations probably breaks down into simpler operations that the programming language helps us put together. They might come in packages and APIs, and then those in turn are translated into eventually something called machine language, the actual commands that we give to our microprocessors. These might have commands to add or subtract, divide, move data around. We simply trust that the microprocessor and all the compiling stages that got us there know what those functions mean because they're routine to define. They're somewhat simple, so adding up binary numbers is so well posed that we can make a machine do it for us. We no longer have to think about it. We can abstract the concept. This is the nature of functions the way that many of us use it, the way of combining them from atomic principles. But there is a question here. Should the standards of the atoms be left to some industry choices based on hardware and costs? Or are there perhaps abstract relationships amongst functions that tell us what should be an ultimate primitive set of functions, ones that would guarantee we can do any program we would ever like, and any steps in logic? The answer is yes, of course. But it looks way too simple to make a chip based on these concepts. We will see that just 3 primitive functions do everything, but they might not be the most efficient at that. So it's always helpful to keep a few shortcuts along the way. What we'll do is simply write this down with a simple language. We'll use certain capital letters to indicate these primitive functions. In some sense, they have no meaning whatsoever. They're just letters, and we'll string them together to mean roughly the composition of these two functions. Do one, then the other. But there's a key difference here. We will have no input variables. Now that's not entirely true on the slides. In order to bridge our understanding with functions we've seen before and these new combinator functions, I will depict some with variables, but that's not part of the axiomatic definition of combinators. That's simply a way to bridge our understanding. So what we need to do is come up with a set of primitive functions that don't depend on variables and that simply attach meaning over how they connect with each other. That is, when we string functions together, they start to behave like the logic we're predicting. So here's our first example of an atomic function. It's the well-known identity functions. Each input returns the same output. We could have it on the real numbers. Each real number x comes out as the real number x again, and it's the line along the diagonal. This is a very familiar example of the identity function for the reals. We could also write this without the y. That is, we don't need to name the function. We can simply give it as what we call a lambda, an abstract relationship of a bound variable x to its output. X maps to x, or in the lambda notation, lambda x dot x. We could also think of this with a specific name like I to emphasize the identityness of this. This is no different than y equals x. But now, writing I of x, we start to think more like the concepts of category theory. The inputs are based on whatever domain we're given in this context. But the real question is, what's missing in this? The first one is, really, I have not said anything about a domain. While I've drawn a picture using the real numbers to implicate this particular identity function, notice that the simple task of replacing x with itself is true no matter what domain we have. We actually don't need a domain at all. This is far more primitive than any concept of functions based on sets. We don't need to know anything about inputs to know how to repeat them as the output. This is a liberating observation. It means that if we take this concept of identity, we might predate any kind of concepts of sets or even types. It's a simpler, basic notion. It's one we can write even at the foundations of our logic, one of our meta principles. There's also no codomain. This simply returns whatever type of data the x was. We don't care whether that forms a set or not. We just care that we have something symbolic to write at the end. And when we take that point of view, that there are no domains and no codomains, then there really is only one identity function. Now this comes counter to all of set theory and category theory that you may have learned. We think of different identity functions, one for each set, or one for each object in the category. None of that is true on the level of true foundations. Now, it's helpful, and we'll see that in future units on type theory, to have some notions of dividing identities up so we don't confuse ourselves and make programs that don't make sense. However, the identity function is really truly unique. There's only one operation being asked for: take X and return it unscathed. That does not depend on anything, and therefore it is a single function. This will become the nature of a lot of combinators. And so we can now write it without any variables at all. Well, let's take pause. We do see a variable v. Let's see how that works. We'll want to characterize the identity, which I've written in bold I, as simply the function which, when I attach to any other function v, returns that function v. Now, I actually don't have notions of inputs and outputs, or returning, or composition. None of that. Those are words we use when we think of functions in the more lambda-centric point of view. And a lot of programming languages have adopted that. But notice what we've really done is introduce the symbol equals. We're simply asserting that the symbol equals will mean IV equals V. We're allowed to replace it, something known as the Leibniz law. Equals is not implicitly understood as already existing. We are defining it. This is a form of reduction. It's reducing the number of variables, the number of letters in our combinators. And this is a weak one in the sense that we're assuming very little. V here could be replaced with any other function, any other combinators, even a string of them. We don't think of it as the input to identity, it's just more like the composition. But again, it's really just a bunch of letters and the rules for rewriting them. And once again, we don't have functions, just one. So let's consider this concept of atomic functions that are constant. We can see the line y equals 3 as a clear example, but we could move that to other places. We would soon articulate that the names of the functions don't matter. We just need to be able to give us the input and the constant that it outputs. There's still no domain and range in that concept. Whatever the constant is, a smiley face, the number 7, pi, all of those are great examples of constants, but they don't actually care about what set they might come from. They don't even need a set. They are, in a sense, free of domains and codomains. More abstractly, they won't even be present in our definition of k. K will be defined without any input and output variables. But there is still one function, and the reason is that the c and the x are just simply two inputs. We need to tell you which constant we mean. So the truth is, there's not several constant functions, there's one constant making function. When we apply it to certain inputs, it can behave like a constant function for the variable x. But again, that's a point of view that only makes sense when we cut things up into their inputs and outputs. And combinators are trying to avoid that. It helps with their logic. And so we can now characterize these functions through the following string sentence. It's a second reduction rule, and it's also weak in that we're not making extra assumptions here of doing one after the other. Here we take two variables u and v, two other combinators that precede k, and the rule will be that when they precede k, k will simply reduce to u, the first one. This is the idea of replacing it with a constant. Now the constant could vary and become a very interesting function indeed, so the result is no longer simply a constant function. We've composed it with a lot of other operations. And now we reach the most exciting and perhaps the most daunting version of these, the S combinator for strong composition. Here I'm not going to be able to draw it until we've explained it a bit, but I want us to think instead of a program as a function, simply taking inputs and manipulating them. Perhaps the most important step in any program is to have a decision, a branch, an if-then-else. Even things like while and for have inside of them a version of an if-then-else. If we can encode these functions, we'll be on our way to producing any function we want by combining them in some order. If we look at this particular structure, we could see out of it a version of this S combinator. On the left, we have a program which is trying to branch based on some property p. That property P does not show up on the right formula in mathematics because it's hidden inside of the ordered pair. When I write something x comma y, it's actually an if-then-else in disguise. We're saying if you select the first component, you see x, else you select the right component and you have y. If-then-else and ordered pairs being the same is a key insight to what the relationships are between logic, which has to predict how things work with implications, and Cartesian sets. This will be part of what's known as the Cartesian closed category, a way of relating implications to Cartesian products. But that's for another lecture. What we have here is a new combinator S, which is combining some functions with inputs in this much more creative way and letting us have the logic of branching. The outcomes do depend on the specific pieces F and G, but the final result can in fact take into account the entire branching, not just individual terms. And if we break this apart, we'll see that this S combinator can be thought of as a two-step process. One is to take a variable x and expand it into an ordered pair, x comma g of x, and then apply f. Now the downside with using this approach is that both it creates the need for an individual combinator to first expand into this diagonal, and then still has to apply f to these pieces. Gluing them together makes a more efficient process. Fewer logical symbols means we can make the axioms more simplistic. And here's an example of applying an S combinator, the strong composition, all the way through. We'll begin with an identity function. We'll apply a function which turns it into parabola, squaring. Now this interpretation is assuming the real numbers as a domain so that I can draw a picture. But the concept of just writing x twice can be repeated in any substitution model. Whether it makes sense as a graphic, that's another operation. Finally, we apply something like the derivative to this function. Again, this can simply be thought of as symbolic manipulation. For example, bringing the 2 down in front of the x. That might not mean anything if we're using different types of inputs, but in the case of real numbers, it means we get this new function, the line of slope 2. This is a brief demonstration, but the if-then-else is perhaps the much stronger reason to think about this. And so we arrive at our last reduction rule. It's again simply to write down what S must do on any other strings. Here we need 3 inputs, the F, the G, and the X. Well, they're now generalized to whatever other combinators we have. And we see that we're going to apply a combination of things. We have both the if and the else part of this formula in U to W and V to W. These are nested inside of each other, and so they all get applied together. The U is ultimately eating everybody. Whether you think of these concepts as your best version of functions, be mindful that they are in fact going to be an equivalent version of whatever type of function you want to think about. We have this very simple summary now of combinators. In fact, on the left, we should even remove the letters X and F and G altogether. Really, all we need are their names, I, K, and S, and the weak reduction rules, which we see simply as the 3 we've seen before. That is a very simple start to function theory. If all we need are 3 letters with 3 simple rewriting rules, we start to behave with an algebraic point of view. We see a sentence and we start applying these rules to reduce it. Reducing is the process of evaluating a function. And here are the gist of where we go with this next. If you use these SKI combinators, SKI combinators, we call them pure. They're pure in the sense that mathematically they are enough to reach all computable functions, all functions by some people's definitions. These, in fact, are useful because of that generality. However, it is often the case that you want shorter formulas. You want programs that run more efficiently. You'd like to rename steps that you've done before and give them shortcut names and apply them recursively. Other functions do exist that are called combinators, even though they might be supplied in some long sequence of SKIs. One of the main examples is things for recursion that rely on fixed point theorems. These will be something like the Bernays R or the Turing Y combinators. There are many other choices out there too. Combinators that aren't part of SKI are called applied combinators, and they would, in some sense, include all of your x86 commands on your computer's microprocessor. These are the starting point to building out assumptions based on these functions existing and not worrying about why they are functions, but building your functions on top of them makes you reliable about being a function yourself. That basic understanding takes furthermore practice, and a good source to start reading would be Hilden and Selden's Lambda Calculus and Combinators. Or search around on the web, but keep in mind the word combinators out there might not mean what we've said here, even though it does have some of the original spirit. Keep looking forward to our next talk where we'll be discussing reduction algorithms and what it means to actually evaluate a function. This is where we'll merge the concepts of lambda calculus with combinators, and it'll lead us eventually to simple type theory.